Hey folks, I'm Sushant and I'm going to talk about migrations. Now, personally, I don't think running migrations is fun, so that's why I want to discuss a few tips and tricks for speeding up migrations, but also doing that safely. So, once we've gotten used to these techniques, hopefully the process will feel a lot less intimidating. So, the tools and techniques that I'm going to talk about would generally apply to most types of migrations, but I want to focus specifically on API backends, uh, backends that host endpoints that are available to our customers externally. And that's because I think migrations of such backends should be done with zero downtime. So our customers might be in different parts of the world, in different time zones. So it would be good if we don't have to put our service in maintenance mode and make it unavailable to a certain group of users. At the same time, if our customers are using our service when we are actually migrating, it would be good if those users do not see any type of service disruption, do not see any errors in our system when the migration is happening. So these are two ideal goals for the migration, but we cannot just build a new system in a vacuum and try and cut over to this new system when we think it's ready. So we need to come up with an incremental migration plan and also monitor the new system as we start incrementally shifting traffic towards it. So we also need to take a data-driven approach to this migration. So one common pattern that can be used for migrating is the Strangler pattern. Now, the inspiration for the Strangler pattern comes from a species of plants called a Strangler fig, whose branches start growing on top of other trees. So it starts growing downwards, tries to grow down to the ground and build its roots there. So as it's growing downwards, it wraps around this particular host tree, uses it for support. And there's a chance that because because the branches of the strangler fig compete with the host tree for light and perhaps nutrients from the soil, that the host tree might itself die. So if the host tree dies, what's left is what you see in the last figure here, which is a hollow central structure, which is the strangler fig. So we can apply the same, we can apply this to software as well, where we can wrap new functionality around a legacy system. We can do that by introducing a facade, typically called a strangler facade, which is going to intercept the incoming requests and based on the configuration, send it to either the legacy backend or the new backend. And once we see that the new backend is behaving as expected, we can gradually start shifting more and more traffic to this new system and eventually cut over to this new system and deprecate the legacy system, which we see in the last figure here. So this is called traffic splitting or traffic shifting as well. And we can do this at just the request level. So for example, if we configure 50% of the requests to be sent to the new backend, there's a chance that there's a 50% chance that the incoming request would be sent to the new backend. However, we can also do this at a user level so that 50% of the users always are directed to the new system. So all of the requests would go to the new system instead of the old system in this case. Another thing that the facade lets us do is traffic shadowing or traffic mirroring, where we mirror the incoming request and send it to both the legacy and the new system. Now, the difference between shadowing and splitting is that we do not use the response that we get back from the new system, from the system that we are shadowing the request to. As you see here in this figure, the facade is making a parallel call to both legacy and the new system, but it's only using the response that it gets back from the legacy system. The response from the new system is going to be discarded. We can, however, compare the responses in the facade. We can also look at the latency of the new system and make sure that that is also within bounds. So this is a really good step for early validation of the new system. And it also does not affect any of our users because they're still getting responses back from the legacy system. Another benefit of this is that because we are mirroring the requests in real time, we can, in theory, mirror 100% of the production traffic, and we can test that our new system can withstand the typical traffic spikes that we see in production. Something to note in this step, however, is that you should be tagging your shadow request appropriately to prevent polluting your production or production analytics data. Or if you are propagating those requests to some other upstream systems, your upstream system should know that these are not actual production requests and they should not be double counting any of that. So with this background, I want to talk about how we migrated one of our backends that hosted critical endpoints for Lyft. If you're not familiar, Lyft is a single smart app to get around your city. It has everything from shared rides to extra large vehicles to bike, scooters, and transit information available in the app. It's currently available to 95% of the population in the United States and in a few select cities in Canada as well. And I work on the purchase flow team at Lyft, which is responsible for showing users all the relevant transportation options for their particular trip. So when a user enters their destination based on their origin and destination, we figure out all the transportation products that are available to them. We fetch the we fetch the price and pickup and drop off information for them, and we build what we call offers. And then we personalize those offers for the users based on their history with the app, based on their preferences, and send this list back to the client or the app, as you can see here on the right. So as you can imagine, this is a critical backend for Lyft. If this backend fails, if it returns an error, then our users will not be able to make progress within the app. They will not be able to request any rides. However, the backend that we had running for this had a few performance and stability issues, and we also wanted to improve or reduce the time it took to build new features on our platform. So we came up with a new architecture for this backend, and we decided to build a new microservice and started preparing for its migration to this new system. So the first phase of starting that migration was adding the Strangler Facade that we previously looked at. In this case, we could have used an HTTP proxy, but we decided to build a gateway service in Go. And that was because we wanted to integrate with our existing experimentation system. We wanted to use that for traffic splitting, more specifically, splitting the traffic based on the user IDs in our system. Another benefit of using a gateway was that we could use our logging and metrics infrastructure. So we could compare the responses of both the legacy and the new system in real time and fire metrics or fire log events, which we could look at. And that helped reduce our iteration loop when we were building the new system. And it also helped us avoid building additional infrastructure for persisting the requests, for persisting the responses from the legacy, and then replaying all of those requests on the new system and comparing them offline. So we could do all of this in real time. So in this phase, all we did was we just introduced the gateway, and it simply proxied all the requests over to the legacy backend. And we did this because we wanted to ensure that introducing another service, introducing another network hop does not affect our performance, does not affect our end-to-end latency much. And our product metrics still look pretty stable. So this was a simple but still a critical step in the migration. So the next phase of the migration was shadowing. So we started building this new system, we deployed it, and once we had all the initial endpoints working, we started shadowing a few requests to the new system. So one thing to note here is that we kept the databases separate between the new and the legacy system, and we were able to do that because we had decided to split the traffic based on user IDs. So once a user ID gets assigned to the new system, only their session level data would be stored in the backend, so in the database. There was no requirement for the new system to be looking at records in the old database. So we could keep them separate, and this simplified our design. And then once the gateway started making these parallel requests, once it started shadowing the request to both the legacy and the new system, we could compare the responses, and if there were any discrepancies, if there were any mismatches, then we could fire the metrics, and we could also log all these events and look at the differences and fix the issues in the new system. So the code for that would look something like this. So this is a snippet from a shadow package that we built internally. And all this does is it basically calls the primary method, or the method that's calling the primary backend, which in this case would be the legacy system. So it calls it in the main routine, but it also runs another Go routine in which it calls the shadow backend, or the new backend in this particular case. So for calling the new backend, it uses a detached context. Detached context is basically a context with the shadow timeout, which can be different from the timeout that we typically have for the legacy backend. And that particular context ignores the parent's done channel. So even if the primary backend responds faster than the shadow backend, we still let the shadow backend continue processing that request. And once that is done, then we can run the callback method. And in the callback method, we can compare the responses from both the backends. So this still does not affect our production latency, and we can still compare the responses from both the backends and ensure that the new system is working as expected. And this is what the RunCallback method would look like, which simply waits for the primary backend to be done, and it's going to call the callback method that we have set on the runner. So shout out to Parker, my teammate who wrote this package. It's a simple but really elegant package that helped us during our migration. And this is what the fetch offers method in the gateway or the facade will look like. So if you remember, offers are all the transportation options with all the real-time information. So when we want to fetch offers for our clients, we can look at the proxy mode variable. So this would be configured in our, this would be set in our configuration system. and its value will be the percentage of traffic that we want to shadow. So if it's set to 50%, for example, then there's a 50% chance that proxy mode for that particular request is going to be mode shadow. And if it is mode shadow, then we will call the shadow package. We will set the uh, primary backend to be the legacy one and the shadow one to the new one. And we'll call the compare results method, which is defined on the state here. And as you'll notice here, we are only returning the response from the legacy backend. So even if you if you don't want to write the shadow package on your own, there is a GitHub, there is a library that was open sourced by GitHub. It's a Ruby library called Scientist, but there are Go alternatives for it as well. So you can check them out and you can use them if you want to do shadowing and you want to compare responses between two methods or two backends. And so what the compare method would do is it would fire metrics, and we built charts for using all of those metrics that we monitored during our migration. So as you can see here, this chart shows the match percentage for the status codes that we get back from both the backends. And in this case, we were at maybe 99.95% at of status matches, and the differences that did exist were all known and understood. So I guess in one case, the legacy backend was returning a 401, which is an unauthorized status code, but the new one was returning a 403, which is forbidden. But we thought that the 403 was more appropriate for that particular case, so we continued using that. And the next chart actually showed us the status codes. So if we would hover over this particular chart, it will tell us what the status code from the legacy backend was, and also tell us what the status code from the new backend was. So we could look at different use cases or different edge cases that we had not considered in the new backend and fix the errors appropriately. So for example, if the legacy backend would return a 400, which is an invalid request, but the new one would return a 200, that would mean that we have missed a particular edge case and we need to fix that in the new system. And we were also monitoring latency of both the backends. So the green line here is for the new backend, and you can see that it's a few hundred milliseconds better than the legacy system, which was according to our plan, because we were using, or rather because we had re-architected some of the code in the new system. This was as expected. So based on all of these charts that we were monitoring, we were confident that the new system was behaving and performing as expected. So that's when we moved to the next stage of the migration, which was the traffic splitting stage. And that's when we began the incremental rollout. So up until this phase, we had to maintain feature parity in both the systems as well. So if we wanted to update or add new features in our product, then we had to add them to both the systems. But once we started the incremental rollout, we added new features only to the new system. And because we were using our existing experimentation system, which we typically use for A/B testing other product features, we could use the legacy system as the baseline for all of those experiments. And the experimentation system gave us detailed product metrics and helped us ensure that the product metrics are also trending in the right direction with the new system. And so in the splitting phase, this is what the code in the gateway would look like. So going back to the switch case that we'd seen earlier, here you see two more cases added to the switch case. The first one is the reverse shadow case where we swap the backends. We did not really use this particular case, but it's just to demonstrate that you can do a reverse shadow using the shadow package as well, where you shadow the request to the legacy backend and make sure that the new backend is still sending the right responses back. But you'll see that we are returning responses from the new backend. And the next case is actually where we are sending all the users' requests to the new backend. So the value for the proxy mode variable would now be evaluated based on the current on whether the current user is in the control or the treatment for our migration. So if they are in the treatment group, that means that their request needs to be directed to the new backend. And so that's how we incrementally started shifting more and more users to the new system. We basically added more user IDs to the treatment group, and we expanded to more regions and more users. And we eventually cut over completely to the new system and then deprecated the legacy system. We could have also retired the gateway, but the gateway we built some additional functionality in the gateway, so we still kept it. We have kept it around, and it's right now all it does is it proxies the request to the new system, but has some additional responsibilities related to API, like some basic authentication and some content negotiation as well. So in conclusion, you can use the Strangler pattern to run an incremental and data-driven migration. You can use the traffic mirroring or shadowing phase to do some early validation of your new backend, making sure that you fix all the issues early, and you can validate the performance of the backend as well in that particular phase. And then once you're confident that the new backend is working as expected, you can gradually start shifting more and more traffic to the new backend. Validate the end-to-end flow, ensure that your product metrics are still trending in the right direction with the new backend, and then finally cut over and deprecate the legacy system. So hopefully you had some good takeaways from this presentation. Please do send your questions and feedback to my Twitter handle. And thanks for joining my session.